starting with the main parts of Chapter 5 then. The atom, we now have the scanning, tunneling microscope that we can use to look at atoms. However, we don't know everything about atoms yet. Rutherford's model, the atom's mass was concentrated in the nucleus, electrons move about it. The model does not explain where those electrons really are. It doesn't exactly say how they're arranged around the nucleus. It also doesn't tell us why negatively charged particles, like an electron, aren't pulled directly into the nucleus. Opposites attract. So how come these negative particles aren't pulled right into the nucleus? Why does that not happen? So in the early 1900s, so scientifically this is not very long ago, in the early 1900s scientists started looking at elements a little bit more. They started looking at visible light when they were heated in a flame. There's a lab that we can do with that. Also light that's given off by stars and different elements also. Once they studied, so analysis of this light revealed that an element's behavior is related to its electrons. So basically how the electrons are arranged in your atom is the most important part for why it behaves the way it does. Is it reactive? Is it non-reactive? Does it give off light? What color of light? So those electrons, what we're going to talk about is we can look at electrons as waves, and that's what we're going to do first. Or we can look at them as particles, but we can't do both at the same time. So if we look at them as a wave, all light, visible light, also X-rays, your cell phone radiation, all of that is a type of electromagnetic radiation. So anything that is electromagnetic radiation is a form of energy that travels as a wave. So your cell phone towers pick up electromagnetic radiation. Your TV towers. What else? Anything that travels as a wave is going to travel through space. All waves can be described using similar characteristics. So wavelength, this is one that I said I think you should know. Wavelength is just basically the distance from crest to crest. So wavelength is the length of the wave. How long is it? So it's from here to here. Or I could measure from here to here, as long as I'm measuring in the same spot. The crest is the top, the trough is the bottom, and then wavelength is the distance of the wave. Frequency is the number of waves that pass a given second. So if you're laying on the dock at the lake and you hear the waves splashing up against the dock, that would be the frequency of the waves. The only thing with frequency here is it's measured per second. You probably don't do that when you're laying on the dock. The amplitude then is the height of the wave. So if I look at amplitude, this is called like the resting line. So if I'm thinking of water, this would be where my water line is at if the wind isn't blowing and I have no waves. It's the resting point. So the amplitude is from that midpoint to the top of the crest, or from that midpoint to the bottom of the trough. I can measure it either way. So when I'm looking, there's all sorts of different kinds of waves. I can look at colors. I can look at X-rays. I can look at gamma rays. We talked about those last chapter. These characteristics will change a little bit with each one. If we're talking about sound, if we talk, Mr. Danick's low voice would have a very long wavelength. My high-pitched squeaky voice would have a much shorter wavelength. If you're yelling and I'm crabby about you guys going to the bathroom, then my wavelength is going to be much taller. You force a lot of air, that wavelength is taller. Or that would be a brighter light, if we're looking at light. So the wave can show you all different sorts of things. The speed of light, let me get rid of all my other stuff here. The speed of light is 3.0 or 3 times 10 to the 8th meters per second. And that's the product of its wavelength and frequency. So C in this equation stands for the speed of light. And the speed of all waves is going to be 3 times 10 to the 8th. And then I can use that to calculate the wavelength. This is the symbol for wavelength. And velocity. And if I look at these, it is an inverse proportion. If I have a longer wavelength, so if my wavelength gets bigger, my frequency is smaller. This would be an AM radio wave. AM radio waves are big, and they travel big distances. FM radio waves, so I'm decreasing my wavelength, which means they have to move faster. So wavelength and frequency are inversely proportional. If I increase one, I decrease the other one. So faster waves, slower waves, fast and small, slow and big. So if we look at the sunlight from outside, there's a continuous range of wavelength and frequencies. And this grid is called the electromagnetic spectrum. You can find this in pretty much every chemistry book. I can see that the light that we see occurs right here. Gamma rays, which are very destructive, are over here. Radio waves, which are very common and we listen to all day long, are on the other end of it. I'm guessing that you can't see the numbers from where you're sitting, but there's a picture of this in your book also. So if I look at this, my wavelength here is 3 times 10 to the 4th. My wavelength here is 3 times 10 to the negative 14th. If I am going this direction, what happens to my wavelength? Gets smaller. So on here it says wavelength increases as I go this way. My waves get bigger. Radio waves are big. AM radio waves are bigger than FM radio waves. If I look at frequency, I have 10 to the 4th and I have 10 to the 22nd. So my frequency increases the opposite direction because they're inverse. Which means gamma rays, the higher the frequency, the more destructive they are. So gamma rays, X-rays, there's a reason that you put on the big lead protective vest, because X-rays are not good for your body. X-rays are destructive. You don't want to be exposed to too many. Radio, they say that they're much longer waves and they're not destructive. Microwaves, infrared, this would be like heat from the sun. UV rays are the ones that cause skin cancer and sunburn. So notice the ultraviolet rays have a higher frequency than your infrared rays. So there I can, and even here, Roy G. Biv, you should know. Red, orange, yellow, green, blue, indigo, violet. Those are the real colors of the spectrum. Red has the longest wavelength. Violet has the shortest. Violet has the highest frequency. Red has the lowest frequency. So, real example. I'm going to use my microwave. And I'm going to use it to cook food. Microwaves can also transmit information, but we're going to think about cooking food. What is the wavelength of a microwave that has 3.44 times 10 to the 9th hertz is what Hg stands for. So that's how I label frequency. So I have C equals wavelength times frequency. Looking back a couple of slides, the speed of light is what? 3.0 times 10 to the 8th. That will always be your C. That's the speed of light.
Are we going to have to remember that? Like,
Probably. It might show up on your test somewhere. I will give you the formula, but I probably won't give you the number. Equals, okay, it's not giving me my wavelength, it's asking me my wavelength, so algebraically that's my x. And then it gives me my 3.44 times 10 to the 9th. So to find my x, what am I going to do? Divide. And I would make sure you plug both of those in parentheses to calculate that. Does it show me my answer? Yep. So when I divide, double check on your calculator that do you get 0.0872 or however it's 8.72 times 10 to the negative second. And wavelength is labeled in meters. So wavelength will be labeled in meters, frequency will be labeled in hertz. And I'll stop there for now.